I think
You are the boss.
yeah. Today it's our great pleasure to have Sergey Fomin to tell us about instance geometry in tile surfaces.
Many thanks for the invitation. It's my pleasure to be here. This talk will be a colloquium style talk. Tomorrow's talk will be just a little bit more on specialized, but today's talk, if you don't know anything about the subject, you are my target audience. So this is based on a paper that is available in the archive. We keep rewriting it and expanding. This is an example of a Russian-Ukrainian collaboration, joint work with Pavlo Pylyavskyy, University of Minnesota. So the subject of the talk is linear incidence geometry. What is linear incidence geometry? It's a study of incidence theorems about linear objects, right? Points, lines, planes, subspaces, projective or affine. And we don't care about distances, areas, anything like that. We just care about relative position. Right? So that's here. This picture illustrates one theorem, particular theorem of linear incidence geometry. And what that theorem says is that if all triples of lines that look like they're intersecting at the same point, or in this case, even 4 lines, but okay, so if you have all these incidences, except for a particular triple of lines like this one, let's say this is not known and everything else is known, then the remaining constraint is force. So that would be an incidence theorem. The first and oldest theorem of linear incidence geometry goes back 1700 years, was probably already known to Euclid, but it definitely appears in the work of Pappus of Alexandria. And what it says is that if you have 2 lines and you pick 3 points, so any 2 lines, pick any 3 points here, any 3 points there, then connect them in the way shown in the picture, then these 3 intersection points will lie on a line. So that's the Pappus theorem.
He could not have proved that without knowing that R is commutative.
Right, we will discuss that also. Thank you. Good point. So anyhow, that's a theorem of Pappus. It took a while until the next theorem of linear incidence geometry was discovered. It's much more recent, just 400 years ago, roughly, due to Desargues. Just like with Pappus, we don't have surviving portraits of Desargues. And what this one says is that if you have 2 triangles in the plane, which are perspective from the same point, so when you look from here at the red points, they completely block the view of the blue points, then the corresponding sides of these triangles intersect at 3 points which are on a line. So this is the Desargues theorem. I presume most of you have seen it before, but of course, theorems like this also occur in other dimensions. And in dimension 3, the most basic, like the first non-trivial result of linear incidence geometry is perhaps not as well known. That's a theorem of Möbius, nearly 200 years old. And what it says is the following. If you have 6 points in the space, right? Let's think of those 6 points. So these are arbitrary points. They don't have to be in convex position or anything. And in fact, they could be complex or some other ground field, but let's think about them as being in R3. And let's think of these 6 points as being vertices of an octahedron. Again, it doesn't have to be a regular octahedron. It doesn't even have to be in convex position, but this is just a mnemonic device for us to think about, collections of points. So the octahedron has 8 faces, as the name suggests, and each face is a triangle. And those faces can be colored in 2 colors, green and pink. And so we have 4 pink faces and 4 green faces. So each of these faces determines a plane. And as you know, 3 generic planes in 3 space will always intersect at a point, but for 4 planes to intersect at a point, a little miracle has to happen, okay? So the Möbius theorem says that if the 4 green planes intersect at a point, then the 4 pink planes also intersect at a point. Of course, some genericity assumptions have to be added and so forth. But generically, this is the precise statement, has many different reformulations, but that's the first non-trivial result of 3-dimensional linear incidence geometry. Okay, so when you see theorems like this, it's natural to ask, and of course, many more of them have been discovered over the years, and books have been written, mostly in German, about this compendia of such theorems. What is really going on? Is there some kind of system behind these theorems? Where are they coming from? Okay, and the most surprising aspect of this project of ours, of this work, is that apparently this has been an open question. Like there hasn't been, this was a cottage industry of sorts that produced many such theorems, but there hasn't been a unifying theory that would explain all of that in a satisfactory way. And of course, another natural question is what kind of other mathematics is this related to? Of course, you can only answer that question if you answer the first question, right? Because otherwise, it's not even clear like what we're talking about. So in this talk, I will try to answer these questions. So let's start with a bit of history. The 19th century was the golden age of projective geometry. People like Jean-Victor Poncelet, Michel Schall, Jakob Steiner, and Karl von Staudt produced the classical body of results. And this was summarized in the very first sentence of Erlangen's program by Felix Klein, who asserted very boldly that the development of projective geometry is the most important achievement of the last 50 years in the field of geometry. And Hilbert, a few decades later, stated that projective geometry has occupied central position in geometric research. The theorems relating to incidence, of course, he meant a little wider array of results, not just linear subvarieties, but arbitrary degree and also Schubert calculus and things like that. But still, the sentiment was that this is by far the most important part of geometry. But then something changed. Of course, every golden age comes to an end. Here is a quotation from Paul Dirac, the famous theoretical physicist who was a big fan of projective geometry. That the field had its heyday, then gradually faded away. All the elementary results were worked out. There wasn't any new work for mathematicians to do. And somebody who works here, Bob McPherson, in his paper with Mark McConnell, nailed it down even more bluntly. Classical projective geometry was, notice past tense, a beautiful field of mathematics. It died, in our opinion, not because it ran out of theorems to prove, but because it lacked organizing principles by which to select theorems that were important. And also, it was isolated to the rest of mathematics. So notice that he's precisely diagnosing the two main problems that correspond to the two bullet points that I made, that there is no system. So it's not just my opinion, it also was Bob's opinion at the time and many other people, that this was just a hodgepodge of kind of Olympiad style statements, recreational math, maybe some, something that is useful as a playground when you teach high schoolers mathematics, but there isn't a real theory behind it, and it's not clear what sort of real mathematics this is connected to. And so I'm going to show you how we bring sort of classical projective geometry back from the dead, right? As Mark Twain once said famously, the announcement of my death was somewhat premature, and explain what is really going on here. But before, let's talk a little bit about what happened in the intervening decades between Macpherson's pronouncement and today. The thing that kind of sealed it in the minds of mathematicians, sealed the fact that there is nothing there to discover, was Manyov's universality, right? So when Manyov proved that representation spaces of matroids can be arbitrarily bad, like the Murphy's law, and then Peter Short soon thereafter used it to show that realizability is NP hard, even in dimension 2 of the reals. So people drew the conclusion that this is kind of provably hopeless, that there is no general theory, because if there were one, this would explain what's going on in terms that would enable us to create sort of polynomial algorithms for deciding, that would produce these theorems that decide whether something is realizable or not, which is basically a statement of linear incidence geometry. So we will see that this was a rash conclusion. On the bright side, the development of computational commutative algebra, things like Grosvenor basis and various algorithms based on them, created a situation where you can prove any theorem. If I bring it to you on a silver platter, you can just type it into an existing off-the-shelf software, and the software will check whether the theorem is true or not. Okay, so verifying, of course, granted, Berger's algorithm is actually not polynomial, and just like simplex method is not, but in reality, it works very fast, and at least when a theorem is such that you can actually draw a picture and make and the number of lines is not 100, but just like 15 or something like that, and then these algorithms work instantaneously, essentially. I'm yet to see a theorem whose proof cannot be delivered, within seconds. And the proof is, a certification. It's some identity from which, of course, you can deduce, if all terms of the identity vanish, it's some identity involving Euclidean coordinates. If all terms are 0, and then the remaining term is also 0, which is exactly the kind of statement that we are looking at, right? So that's great, but it doesn't really explain anything, primarily because the problem is not in how to prove these theorems, but how to make sense of them. Where are they actually coming from? How could we today invent Desargues, Pappus, Möbius, and scores of other theorems that you can find in the literature. So to recap this introductory portion of the talk, the key questions are, where do the classical incidence theorems come from? Which of these theorems are important and why? And what kind of other mathematics are they related to? Of course, mathematics is such that once you connect it to one subfield, then it will be connected to everything else. It just happened to be in an isolated, small connected component, and now we connect it to the giant component. We will connect. So the way I'm going to answer these questions is by establishing what we call a master theorem of linear incidence geometry, from which various, perhaps all incidence theorems can be obtained in special case. And again, I will only be interested in the classical situation, working over the reals, or better yet, over complex numbers. Just, you know, nothing exotic, just exactly the theorems that you want to study in high school. And this would provide a new unifying perspective on this subject. So the way this will develop is through tilings. So we will consider tiled surfaces. So take an oriented, two-dimensional, Riemann surface. So just in topological category, just viewed up to homeomorphisms. And we want to tile it by quadrilateral tiles. Okay, by tiling, I mean, like no funny business, this is like, not just, this should be a CW complex, you can have a vertex in the middle of a neighboring tile and things like that. So everything is kosher. Okay, I'm sure you can write down formal definition what a tiling is. Here are some more tilings. In fact, each of these pictures has two tilings. So I will explain how any such tiling endowed with bipartite labeling of its vertices, which is not always possible, but almost always typically possible, will give rise to an incidence theory. So let's now do some math. Suppose we have a finite dimensional projective space P. A tile is just a quadrilateral, but I will label its vertices by points in our space and hyperplanes, which I will interpret as points in the dual projective space. Okay. So there will be white vertices and black vertices, and I will put their, points in P star and P respectively. And this is the main definition, so please pay attention. A tile is called coherent if, well, the first is a genericity condition. So unlike you might have thought, I don't require this point to lie on this hyperplane. In fact, I don't want it to lie on that hyperplane. Okay, so this is an open condition. And this is an important one. Again, this is not going to happen generically, so let's ignore this. Here's the key condition. I want the line AB and the codimension 2 subspace L intersect M to have a non-empty intersection. Okay, so AB is a line. L and M are codimension 1 things, right? So when we intersect them, we get something codimension 2. And something codimension 2 and something dimension 1 generically will miss each other. So I want to impose the condition that they don't, that line actually pierces that codimension 2 subspace. Then I call this tile coherent. Okay, is the definition clear? All right. So now let's look at the simplest case when we are working in the projective plane. So A and B are the points, L and M hyperplanes are the lines, right? The hyperplanes, these lines intersect at a point, and I want that point to be pierced by the line AB, right? Which generically is not going to happen, but for a coherent tile, it will, okay? So I want the line AB and the lines L and M intersect at a point. Or equivalently, I want the point A, the point B, and the intersection of L and M to be collinear. Okay, is this clear? That's the condition of coherence. All right. So now the master theorem comes. Let's take a tiling of a closed oriented surface by quadrilateral tiles, and the vertices are colored black and white, but in a bipartite way. This picture here shows a torus. I mean, it's a hexagon, but the assumption is that you glue together the opposite sides, this one to this one, this one to this one. Notice that the labelings match. Okay, so if you take a hexagon and you glue together pairs of opposite sides, you get a topological torus. Okay, this is a tiling of the kind that we consider. So now I'm going to place a point, respectively, or associate a point, respectively, a hyperplane in my projective space to every black, respectively, white vertex, and I want it to be generic in the sense that it should go. Okay, so far nothing really has happened. So I just want you to have the right picture. So there are two realms, right? It's like in a Fourier transform. You know, there is the topological realm in which I have this surface which is tiled, and then separately somewhere in a different universe, there is this projective space where the actual sort of incidence geometry is taking place. So this topological surface that I tiled serves as a blueprint for describing an incidence geometry statement. Okay? Okay, so now the punchline, if all tiles in the tiling, with the exception of one tile, are coherent, then the remaining tile is also coherent. Okay, so that's the theorem. Now this theorem is not hard to prove. The hard parts are first coming up with a theorem, and second, actually showing that the theorems that we all know and love are special cases of it. And I will demonstrate that. I will start by proving the theorem. So it's often said that every talk should contain at least one proof. In this case, it's the proof of the main theorem. The entire proof is very short. The key observation, which you can easily verify at home, or some of you maybe can do it in your head, is that the coherence condition is equivalent to requiring that the mixed cross ratio of those four objects is 1. What is a mixed cross ratio? So you have 2 points and you have 2 hyperplanes. You draw a line through those 2 points. That line intersects those hyperplanes at some 2 points. So now you have 4 points on a line. You compute that the cross ratio of those 4 points in a certain order, when it's certain cyclic order, which is given by, determined by the cyclic ordering of these 4 objects. And since I'm saying that it's equal to 1, so when you invert the cross ratio, it's still 1. So, you know, there are like many different versions of a cross ratio, but in this case, it is all canonical. So so that's the claim. And how do we define this cross ratio? You know, the way usually it's defined. So A, B, L, and M are projective objects. When you deprojectivize, A and B become vectors, L and M become covectors. Of course, they can be pairwise. And since A, B, L, and M all appear once in the numerator and once in the denominator, this ratio doesn't change when you rescale A, B, L, and M, and therefore it only depends on their projectivization. Okay, so now an observation is that when you multiply all these mixed cross ratios, the product telescopes, because every pairing, we only consider pairings of black and white vertices that are adjacent in the graph. Okay, and remember they are non-zero, so they can appear both in numerators and in the denominators. And indeed, each of them appears exactly once in the numerator, once in the denominator, because where it appears is determined by whether when you go clockwise around the face, you know, the white precedes the black, the white end precedes the black end, right? So on one side of that edge, the white comes before the black in the clockwise ordering, and on the other side of that edge, it's the opposite. So you get a completely telescoping product, and everything cancels out. Okay, end of proof. Is the proof clear?
We really need orientable.
Yes, yes, that's where we need orientable. And moreover, coming back to your comment, this would work even in a non-commutative situation if the genus is zero, if our surface is a, because then it's kind of a Van Kampen diagram kind of argument, right? And but on a torus, for example, not, because there could be a cycle that is not paved by these, you know, the first homology is not generated by of the graph. It's not generated by.
So you need a higher genus surface to prove Pappus now?
Yes.
Sorry.
This is coming, indeed. That's right, because you possess of secret knowledge, right? The Pappus theorem. Well, which I guess just revealed, right? Exactly. Okay, but let's. Okay, so go back to the talk. So here is the amazing fact that this is enough. You can open your favorite textbook of projective geometry. You look at all the named theorems going back mostly to the 19th century, but some of them to the 20th century. And then you work very hard and you find a suitable surface, and you find a tiling of it from which you get the theorem.
Find the suitable surface by just being smart, or
Exactly. So
no other way.
So the quotation at the beginning of our paper is from Don Knuth, which says that, okay, I don't have it with me, but it says something like, science is everything you can teach a computer. We can teach a computer. Art is everything else that we do. So according to this definition, it requires art, right? So, unfortunately, right? Or maybe fortunately, right? Yes.
I'm just thinking, like, naively, I would expect like the number of points in the surface to be exactly the number of objects in the theorem.
Right.
Maybe this doesn't happen.
No, but it's not far. It's not far. Yeah. I mean, I don't have a precise answer to it because we don't know how to do it. Okay, so let's see how it works. I'm moving much slower. So do I have 60 minutes or 50?
Please take your time.
Okay, I will. Thank you. So, Desargues theorem. Desargues theorem is the simplest theorem of linear incidence geometry, and indeed it corresponds to the simplest possible tiling, namely the tiling of a sphere by 6 quadrilateral tiles, also known as the cube or the surface of the cube. Okay? Now, we want to strategically associate the black vertices to some points A, B, C, D, and the white vertices to some lines P, Q, R, S in this picture, so that then the coherence condition translates into the statement, you know, the ingredients in the statement of Desargues' theorem. So let's take our favorite face. I want to pick the person in the audience, Leonardo. Which of these faces you want?
Top face.
Top
face.
The top face. Okay. A, B, R, S. Okay, so this is A, B. These are 2 points, right? And we need to also look at the intersection of R and S. They intersect here at this point. And indeed, A, B, and that intersection lie in a line. Okay? And you can check.
What's S?
S is this line, but of course, what I want to define S as a line that goes, let's say, through this point and this point. And a priori, we don't know that it also goes to that point, and that condition will be one of the 6 coherence conditions. So if everything else works out, then, but of course, I could also have defined S as a line that goes through these 2 points, and then the fact that S goes through this intersection will precisely correspond to the top face that Leonardo selected, and everything else, the coherence of the remaining faces will describe the rest of the configuration in an equivalent way. Okay, so that's how you get Desargues' theorem. Of course, we can approach this from, you know, going forward, like take various tilings and see which theorems pop out. But that's not what we wanted to do at the beginning. At the beginning, of course, we had the Pappus theorem, and we wanted to get it. And at some point, I thought it was impossible, and then we found out that indeed it is possible. And the reason it's hard, and I believe that's why this hasn't been discovered like 100 years ago, because it's not true that you just need to take some of the vertices, some of the points, and some of the lines of the given configuration. Even though, you know, in Pappus configuration, there are like 10 points and 10 lines, or nine points and 9 lines, right? And so like deciding which of them to take and how to build it into a tiling is also complicated, but even that is not enough. You have to also use a trick. So the trick is that instead of taking these 3 points, the ones that I'm pointing at, you look at the lines of the triangle that they form, and you call those P, Q, and R. Okay? It's the same information. So I'm going to use the points A, B, C, D, E, F, which are from the original Pappus configuration, and the 3 remaining points I will replace by 3 lines P, Q, and R. And then I will consider this tiling of the torus. Okay? And again, like, I don't know, Daoji, which tile you want me to look at?
REPB.
REPB. Okay, so B is a line and R and PR. So PR is this point, right? And it lies on B. Okay, you're right. Okay, so you can go home, you know, you can take the slides, I can send them to you, you can check that everything works out exactly as intended. So if all these conditions are satisfied except for one, the remaining one is satisfied, and that's precisely the Pappus theorem. Of course, you know, modulo some genericity constraints, which, you know, usually people sweep under the rug anyways, right? Because you don't want lots of these points to lie on a line, or any of these lines intersect at a point, or God forbid, you know, coincide with each other or something, right? So generically, we do get the Pappus theorem. Okay, here is another famous theorem of linear algebraic geometry, incidence geometry, the complete quadrangle theorem, made famous by people like Ruth Mufang and Shimshona Mitsur. And okay, what does it say? You can kind of guess by looking at the picture, right? So there are lots of triples of lines that intersect at a point. So if all of them are given, all of these concurrences are given, then the remaining one will follow. Okay, or you can say it in terms of like triples of points that lie on a line. If all those collinearities are given except for the one, then the remaining one follows. And the proof is you just take this tiling of the sphere, there is a back tile, which is also quadrilateral, and you just interpret this and you get that theorem. Okay, so I'm not gonna ask anybody in the audience because these are two separate slides, but you can imagine that if I'm saying something like that I checked it. Okay. So you can sue me if it's allowed. Okay. Here's another famous theorem, the permutation theorem. Again, you can guess what it's saying, and let's say we know that all these incidences take place except for, let's say, these three lines that will follow from the rest, and here is the proof. Okay, so each time a proof is just like in these Indian, ancient textbooks, just a picture, and you just need to look at it and think hard and compare and check that indeed it does the job. But of course, coming up with this tiling, required hours and hours, if not tens of hours of search, and you develop some kind of intuition, and you develop a skill. It's more of a skill of a sculptor or something. It's really not. I mean, you like know that certain things work, and this feels like I need to move this point here, and I mean, I cannot really make it algorithmic. Okay. This is a new theorem, and indeed, I mean, we can generate as many new theorems as we want, right? In the old days, in the Middle Ages or in the Renaissance period, people would actually hide the master theorem and then, publish more and more papers without telling anybody, with proofs that use like Grosvenor basis or something, which don't reveal actually where that theorem came from, right? So if I didn't have tenure, maybe I would have. So here so this is one of the new theorems that we discovered, simply because we wanted to find an interesting theorem that comes from a genus 2 surface. And this is a twin stars of David theorem. So there is a blue star of David and there is a red star of David, and then they're kind of mutually inscribed into each other. You can see which lines intersect at a point, and again, you choose one of the locations where three lines intersect, and you drop that condition, and the claim is that it will follow from the rest. And this is, this is actually, this is genus 1. So this is just a torus, the tiling of a torus. The next one will be genus 2, I think. Oh no, it's coming even later. Okay, I didn't remember. So now, what about higher dimensions? Möbius theorem. That's the proof. You just apply it to this tiling of the torus. Now, some of you might think, like, how do we know it's in 3D and not in 2D? And the answer is, actually, every tiling gives you a sequence of theorems. In each dimension, it gives you a theorem. Each next theorem is more powerful than the previous one. There is a trick that enables to obtain a smaller dimension. Basically, you just intersect with the generic hyperplane, and you get it. So this theorem in dimension 2 is trivial. Like, it doesn't actually say anything. The conditions that you are given de facto include the condition that you want to deduce. But in dimension 3, it's a non-trivial result. and that's the Möbius theorem. This is another new theorem, which is the 13 lines theorem, we call it. So this is for those of you who like Schubert calculus, maybe this is you will like this one. So here we start with 2 lines, you know, and we okay, so we start and we pick 5 points on each of them, and then we draw these 5 lines. Okay, so we start with the red configuration. So generically, you know, 4 lines can be pierced by a line, but 5 lines cannot be pierced by a line, but we assume that they can, and in fact by 2. Okay, and then we play a certain game. We start with this point P1, then there is a unique line that passes through P1 and intersects M1 and M4. So we draw that line, and the location where it intersects M4 we call P2, and then we continue in similar fashion. And after 6 steps, we will come back to the original point. So it's a complicated configuration consisting of 13 lines, and it's one of these Schließungssätze in German, the closure portism, that you do something and you come back to where you started. And there is no way, I don't even know like how one could invent or guess that a result like this holds, other than in the way that we discovered it by taking this genus 2 surface. That's the example, that's what I wanted to say before. And taking this tiling of it, so like this triangle is glued to this triangle, so it's a quadrilateral thing. So in each of these 2 hexagons, you glue opposite sides. Okay, after you do that, this annulus becomes a genus 2 surface, and you get a tiling, and then you interpret that tiling in the way you see the labels here. These H, Ij, and P sub I, they correspond to the P sub i's are these points, and the H's are like intersections of L's and M's. So when you get these slides, if you want to analyze it, they contain enough information for you to be able to recover everything. Okay, so that's good. So we managed, you know, whichever theorems we found in the textbooks, we ended up being able to find a tiling. So that's satisfactory. Of course, as I told you, we don't know if this is always possible. So that's the first open problem. Can any theorem of complex linear incidence geometry be obtained as a special case of our master theorem? Again, one needs to be careful, like what does it mean can be obtained, in which way, like first order logic or something else is allowed, and what do you mean by special case, like are we allowed to take limits? And anyway, I just leave it, I pose it intentionally vague so that to maximize the chances that the answer is yes, because obviously we want it to be a universal.
Why does my field have to be complex numbers?
Oh, because over the reals, we believe the answer is no, because there are statements like you can encode a statement that if x to the x cube equals y cube, then x equals y. You know, over the reals, this is true generically. I mean, just true. But over the complex numbers, obviously, it's not, because, right? And so any identity can be, by von Stau's theorem, any identity can be encoded by an incidence theorem. And so you would have an incidence theorem that says that if, let's state that theorem, that if something holds there, then something holds here, right? And which is a geometric rendition of this implication. It would be true over the reals, but not over the complex numbers. But our technique doesn't see whether it's real or complex. So
that's the Galati theorem is a theorem in linear incidence geometry.
No, it's
Not
not of this kind. Right. All right, because basically these are like first order logic. You are not allowed to, introduce quantifiers, like there exists something with some property.
But the other, I was more asking about the other direction. It looks to me that nothing prevents me from proving incident geometry theorems over F20 something, like finite fields, by looking at some items.
We can talk about this a little bit. There are theorems which are true over F2, like, like Fano matrix, right? But which is not true in general. Whereas this technology is blind to characteristics. So
Where did we use the characteristic 0 or something?
we didn't use it, but I think basically this will typically prove a theorem that holds over any field, but also the genericity conditions themselves, like over F2, you cannot have 4 points, different points on the line, so you will have yeah. Okay, problem 2. Is there an efficient algorithm for constructing a tiling? I already told you that we don't know such an algorithm. And problem 3, what is the meaning of the surface? We have examples where the same theorem can be encoded both using a sphere and a torus, for example. So the genus of the surface is not an invariant of the theorem, but there is a minimal genus in which a given theorem can be stated, and that somehow should tell us something intrinsic about the theorem. Yes?
Does that mean you have examples where you can say the genus is not 0 for this theorem?
Yeah, the Pappus theorem, for example, yeah, is and this is it's a known, yeah, it will become clear why. Okay, so let me now maybe change the speed, because I'm hopelessly behind schedule, but you've been asking questions. So there is another version of this theorem which uses triangulations instead of quadrangulations. So if I have a triangulated surface, in this case a torus, right? This is a rectangle whose opposite sides can be glued. I can take each of these triangles and split it in the way that I've shown. And I do this with every triangle. Then I get a quadrangulation of my surface, right? The black picture gives me a quadrangulation. Okay, so I remove the red stuff, and then I get a tile. Okay, so from every triangulation, you can construct a quadrilateral tiling. From a quadrilateral tiling, you can get an incidence theorem, which means for any triangulation, we can get an incidence theorem. What we get, okay, there will be a corollary. I don't have time now, but there will be some statement now tied to a triangulation, not to a quadrangulation. And when you take the simplest possible triangulation, which is the tetrahedron, this is a triangulation of a sphere, you will get Desargues. And when you take this triangulation of a torus, so a hexagon triangulated into 6 triangles, and then opposite sides glued, then you will get Pappus. And in fact, there is a trick which I don't have time to explain that allows to go backwards. We can recover the quadrilateral tiling version from the triangulated tiling. Okay, let me skip the details. So now remember, the Desargues in the triangulation version corresponds to a tetrahedron, right? So when we replace this by this, we are gluing in a tetrahedron. When we replace this by this, we are gluing in or removing when we go back. So two triangulations that differ by flips like this correspond to theorems that are equivalent modulo Desargues in a kind of simple way. And it's a well-known fact that any two triangulations of a given surface are actually equivalent modulo these moves. So modulo Desargues, we just need to know the surface because all the triangulations are connected by these flips. Okay. Notice we can add or remove a point, a vertex of the triangulation, so we don't have to fix the number of vertices. Okay, so any two incidence theorems come from triangulation of the same surface are equivalent modulo Desargues, and there is a similar statement for quadrangulations because of the equivalence that I mentioned before. So, in fact, all theorems that come from triangulations are equivalent to each other, modulo Desargues and Pappus. We already know everything just depends on the surface. And we know that Pappus corresponds to some triangulation of the torus. And then we can glue in, as many tori as we want. And each time when we glue in, it corresponds to an application of Pappus. Okay. This is, by the way, a well-known fact in the community of geometers. They know that let's say over the complex numbers or reals, every theorem follows from Desargues and Pappus. There is yet another point of view. Instead of looking at quadrilateral tilings, we can look at the dual object. We can connect the opposite sides of each tile by a segment of a curve and then extend these curves across the tiles. Okay? Kind of a medial curves, right? It's a well-known construction. So now I'm slowly transitioning to connections with other fields of mathematics, if you have noticed. So for example, from the cube, we will just get three great circles. And that's Desargues' theorem. So any multi-curve on an oriented surface whose regions can be properly colored in two colors gives rise to an incidence theorem. Because this is cryptomorphic to a quadrilateral tiling. Just put the vertices of the tiling inside the regions and connect them across the sides. You will get a quadrilateral tiling. And your multi-curve needs to be generic, so no triple points, no inappropriate patching. So that's another way of thinking about this stuff. Now, remember that Desargues' theorem corresponds to a cube, right? So application of Desargues in the quadrilateral setting. So an application to a Desargues theorem, by an application, we can go from this tiling to this tiling. So find three tiles that form this kind of hexagon and rotate it 60 degrees inside, right? This is an application of Desargues. What does it correspond to in the language of medial curves? It corresponds to a Yang-Baxter move. That's easy to see. Okay, or Rademacher 3. So these are like these curves that don't go above and below. They're just drawn on the surface. And so there, in addition to this Desargues flip move, there are also simplification moves which correspond to some easy geometric transformations of the theorem. So for each surface, we can study the sort of the multitude of incidence theorems that can be described by these tilings by just looking at equivalence classes modulo these transformations. And in fact, topologists have looked at this and there are results about it. Like what the equivalence classes are labeled by and so forth. Okay, let me switch gears now and talk a little bit about integrable systems. That's another connection. So we can interpret Desargues' theorem as a 3D consistency condition in the following way. If we have a point, three lines, and 3 points, right? And these 7 objects are such that the 3 quadrilateral tiles here at the bottom, 1, 2, and 3, that they're all coherent, then Desargues' theorem says that there exists a unique line here at the top such that these 3 tiles, the 3 tiles incident to the top vertex of the cube, are all coherent. Okay, this can be viewed as a reformulation of Desargues' theorem, and this is called by Babenko and Souris a 3D consistency condition, and they have a whole book that explains why sort of morally this corresponds to integrability of this of the discrete dynamical system that propagates using consistency condition. And according to their yoga, what you need to look at is whether the 4D consistency holds or not. So we take a 4-dimensional cube, we label this by point, these 4 guys by lines, these guys by points, and we require that every quadrilateral that involves the 3 bottom levels is coherent. Okay, suppose that is checked, then Desargues tells us that there is a unique line here, unique line here, here, and here, that makes all the quadrilaterals that live on these 3 layers, second, third, and fourth, coherent. Okay, and then you ask, does there exist a point upstairs such that all the 6 quadrilaterals, because you can choose any 2 guys here, right? All the 6 quadrilaterals adjacent, incident to it are coherent, and maybe that's too much to ask, because these are 6 conditions that we impose. But amazingly, the answer is yes. Okay, and this can be proved by a variation of our techniques, and this is the picture. This is the corresponding incidence theorem that, of course, nobody in his right mind would have come up with if not for this connection and for like of course, first the connection to tilings, and second the inspiration that comes from Babenko-Souris theory. So this is, I'm not going to tell you what exactly is given and what, but like at the beginning we start with this point and 6 lines emanating from it, and we end with these 6 dashed lines intersecting at a point. And I use GeoGebra. This is a freely available software package to actually draw these things, and it was amazing how like I saw that these 6 lines intersected at a point. Like it's really humbling. Okay, so this can be restated in turn as saying that Desargues flips satisfy the Malotchikov's equation, also known as tetrahedron equation. So when we take a tiling of an octagon, each tiling of an octagon contains, these are like zonotopal tilings of an octagon, contains exactly 2 possibilities for a flip, like this hexagon here and this hexagon here. So you do one of them, then you get a new tiling. You could of course go back, or you can go forward using another flip, and after 8 steps you come back to the original tiling, right? And each time you do a flip, the Desargues theorem tells you there is a new geometric object that flip generates, and a priori there is no reason why after 8 steps, when we recover the original tiling, we recover the original geometric objects. There could be monodromy a priori. And it's a reformulation of this 4D consistency of this theorem drawn here, that there will be no monodromy. Okay, so this is yet another connection. So now let me quickly wrap it up. So the master theorem helps explain in a conceptual way why Pappus theorem is more powerful than Desargues, because roughly speaking. You can glue everything out from tori, including a sphere, by the way, but you cannot do it just from spheres. Why Pappus, with or without Desargues, imply all other theorems of planar linear incidence geometry. This is well known. As I mentioned, why Desargues holds over non-commutative skew fields, whereas Pappus does not. How to construct generalizations of existing incidence theorems by tweaking a given tiling. I don't have time to explain, but we have a full section about that. Which incidence theorems can be formulated as closure purisms, these Schließungssätze that I mentioned, and which ones cannot. This is related to existence of some Hamiltonian cycles in the dual graphs of these tilings, and many other things. Also, these techniques can be used to study the pentagram map in its variations, the skewers of Tabachnikov, incidence theorems for circles and lines in the Möbius plane, obviously. More interestingly, incidence theorems for conics and algebraic curves of higher degree. This is what we're busy with right now. We have several versions of this technology for conics that enables us to recover pretty much everything that mathematicians managed to produce in the last couple of hundred years about these gadgets. Incidence theorems involving tangency conditions, we haven't been yet able. No, actually, we know how to prove a famous theorem of Poncelet using this technology. Closure phenomena, many other versions of Poncelet's closure porisms. Of course, theorems for surfaces that we haven't yet started even. Instance theorems over fields of finite characteristic. I mentioned that if somebody asks me, I can explain quickly how that works. Incidence theorems over non-commutative skew fields I already mentioned. Of course, you can try and do it, work in elliptic or hyperbolic geometry, and I'm sure there is a lot more coming up. And that's all. Thank you. Derek?
You didn't tell us one thing,
Okay.
how you came up with your math theorem.
Excellent question. Thank you. So we were actually working on a completely different project that involved the use of tensor diagrams and cluster structures on Grassmannians. And we just noticed some identities that looked kind of familiar but like surprisingly simple. And so, and then once we realized the meaning of that, and once we got the Pappus theorem, then we dropped that project. And if we ever, actually, we have the main result, like we don't have time to write that paper anymore. Now, of course, as it happens, frequently people invent kind of revisionist history, because I have a pitch of like how I wish we have discovered it. Like what was the sort of the right way to come up with this? And the right way has to do with classical invariant theory. I don't know if you want to hear that story or not. So of course, the standard technologies for proving incidence theorems using algebra or a little bit of combinatorics, which have been developed, by people like Sturmfeld, Richter-Gebert, and there is a Chinese school also pretty well developed. So they are based on, encoding an incidence theorem by an identity, right? In a certain invariant ring, typically like a Plücke ring. So, the homogeneous coordinate ring of the Grassmannian, and then, proving it using some kind of, Gröbner reduction or some kind of straightening algorithm or some other algebraic manipulation. And the problem is that when you work in a Plücke ring, you have lots of relations, right? Most famously, the three-term relation that I know and love and June too for different reasons, but this is like the basic one. Product of two things equals product of two things plus product of two things. Okay, so lots of relations of degree 2, and you have to somehow like work with the quotient by the corresponding ideal, right? Now, the idea that I wish we have had, I mean, this revisionist story, right, which is not correct, but this is how we should have discovered it. And we had this in the back of our minds, but is that instead one should work in a ring, in a different invariant ring, in a ring where you use both vectors and covectors, right? So the invariant ring that we just talked about, the Plücke ring, is just the invariant ring of SLK invariants of a collection of n vectors in C to the k, right? So you have k column vectors, and they form a matrix, right? SLK acts by left multiplication of that matrix, and okay, you get Plücke quad. So that's a complicated ring, as I said. You can look at the mixed Plücke ring, which involves invariance of collections of vectors and covectors, which correspond, of course, to lines and hyperplanes. Okay, and you ask only for the total degree 0 homogeneous component. So a vector has degree 1, a covector has degree -1. Okay, there is a grading then. When you pair them, you get a scalar which has degree 0. So that's why you want to grade them in this way. And Hermann Weyl, of course, who also worked here, described these rings. We know what, both the first and the second fundamental theorem. And so there are relations there, of course, even more relations. Okay. But even though there are more relations, they are in much higher degree. Like the simplest, in the case of planar, in the case that corresponds to planar geometry, so that's Grassmannian G3n and corresponding mixed Grassmannian. The simplest relation that these pairings satisfy. So that invariant ring that I mentioned, it is generated just by pairings. You don't need to take Plücke coordinates. You just take pairings of vectors and covectors. And the simplest relation is that the ground determinant 4 by 4 is 0. So that's a relation of degree 4 that has 24 terms. Okay, so you have a ring, also a commutative ring, a pretty complicated one. But the first relation you only see in degree 4, and that degree has 24 terms. So for all practical purposes, you can just ignore it and pretend that those things are algebraically independent. Because if you have a theorem like Desargues that only involves like 9 objects or 10 of each kind, right? You're never gonna get to use a relation that is so far out. So then the question is, you need to work, the hint is you need to work with pairings, just pairing a vector with a covector, right? And you just want to treat them as if they were algebraically independent. But then what kind of statements you can make? Well, the only statement you can make is that, I mean, if certain things multiply to 1 and some, I mean, if one product is equal to another product, which means that the ratio is 1, right? And then another product is equal to another product, then if you wrote it so that like both on the left-hand side and on the right-hand side, the same guys appear, then the last of these things will follow from the rest. And that's really what's going on. And then you realize, oh, but then really like this telescoping can be always described by tiling. This is actually just cryptomorphic to each other. And then you arrive at this. Okay. Yes, Friedrich.
Is it clear that every tiling gives an can be realized by an incidence configuration?
I think, I see. A priori,
I mean, your
right.
your theorem could be void in a literal sense.
Right, so over small, over a small finite field, this would probably be false. We have examples actually like that. But over complex numbers, I believe that yes, the answer is yes. Just for dimension reasons, like there isn't much that we ask. So some kind of shelling, one probably needs to take some kind of shelling of the tiling and then like build this configuration. Yeah, I don't expect. I agree. It's a good question. It's a natural question to ask whether that theorem could be potentially void just because we cannot actually construct it, right? But it seems that it's all working well. Yes.
I'm wondering, can you realize that for the consistency tile, because like it seems to be not a surface?
Right, yes, excellent question. And indeed, we cheat a little bit in the proof. So we have to, right, because it feels, it's like a higher dimensional complex that we are kind of secretly using, right? But so there is a limiting argument in the proof of that theorem. Yeah, good catch. Yes?
In the spirit of the secret knowledge, is there the Desargues flips? Is there a literal way to interpret associativity of the underlying field or algebra from that?
No, well, associativity.
So you can have a non-associative projective plane and presumably.
I never thought about this. I only thought about commutative versus non-commutative.
I think you have to be careful about cross ratios. Cross ratios are pretty important.
They are important though.
Yeah, I don't know, because we are going around, like, right? The technology says that, you know, when you go around so each side, each edge gives you an element in your skew field, right? And we want the product of these to be one, right? But it's not clear, like, first of all, if there are parentheses, then which of them you need to take, and whether it depends on where you start doing it. Right. So, yeah, the non-commutativity is clear, right? So you know this product. It's like with maps, right? You know the product of these maps is one, right? So your diagram commutes along every face except for one face, then it commutes along that face, but it's only true for if it's a sphere, because otherwise you don't know that there is no monodromy when you go around the handle, right? And that's why Pappus theorem doesn't hold over, sort of morally, why it doesn't hold. Of course, we don't have universality, so we cannot really argue that way, but it rhymes with the facts that we know. Okay. Yes, Dauji.
If I have just a stupid, I just have a rectangular grid.
Okay.
maybe do this and do that.
Okay.
What theorem does that?
Okay, so first of all, one should be careful. When you take a rectangular grid and you glue it this and that way, you want to make sure that your rectangle is even by even.
Okay,
Because if it's odd, then, you know, the color of a vertex will change, right? And as you go around, it can change its parity, right? So we want this to be a bipartite graph, okay? Then it will be, yeah, the theorem is not, for small ones, these are known theorems, but for when you take like big enough, it gets, you know, something crazy.
not clear what.
No, I mean, it's clear, you
It's
can
clear.
draw it, but it just, you know, it looks like a mess. You know, lots of, I mean, it's true, I tried it, and you draw these lines and you see what comes out, but somehow it's like not very interesting. The more interesting ones arise when you take a grid, but instead of quotienting it by you know, the lattice, which is just AZ cross AZ, you take some other lattice. You know, just take some two integer vectors, right? And choose a fundamental domain, the parallelogram that they span, and then glue. Okay, so you take that kind of quotient, then you will get again a tile surface. Of course, the parity needs to be checked, right? And then locally it will look just like a grid, but of course it's a grid with a twist, right? So you will have, you know, like you will have a torus which with two sets of lines, right? The lines that came from vertical and the lines that came from horizontal, and they have a certain, you know, number theoretic properties, like, so this, you know, some SL2Z business will come in and we played with that, sorry, and that does give like more interesting things. You know, like one of them, I showed you that there was this Star of David, two stars of David, that involves a particular parallelogram. So yeah, you can play, I mean, there are lots of things that one could do. You can spend the rest of your life playing with different examples and trying to see what happens if you do this and what you do that, and, right? Maybe I will, I don't know what, it's already 3:18, so I want to.
Okay, let's save other questions for the tea time.